Welcome everyone to today's edition of the NITheCS Colloquium. It is my great pleasure to introduce the speaker. Professor Sanne Horst received his PhD in mathematics and operator theory from VU Amsterdam in 2007, complemented by system and control theory training at the Dutch Institute of Systems and Control. Currently, he is a full professor at Northwest University. He serves as editor-in-chief of Questione Mathematica. He is a member of the editorial board of Complex Analysis and Operator Theory, has held various portfolios on the Council of the South African Mathematical Society since 2013, and is a vice president of the steering committee of the International Workshop on Operator Theory and its Application Conferences series, as well as a member of the steering committee of the International Symposia on Mathematical Theory of Networks and Systems. His research focuses on operator theory and matrix analysis with applications in systems and control theory, including metric constrained interpolation, unbounded Toeplitz operators, infinite dimensional and non-commutative multidimensional systems. Just want to add that the journal where Sanne is editor-in-chief, Questione Mathematica, is actually the journal of the South African Mathematical Society, and we also have a pleasure to have his predecessor, editor-in-chief in the audience, Professor Barry Green. We very much look forward, Sanne, to your talk on the convex invertible Cohen approach to Nevanlinna-Pick interpolation.
Thank you so much, Zura, for the kind introduction. It's always nice to be in Stellenbosch, and thanks to everybody who's here at my talk. Yeah, so this is on Nevanlinna-Pick interpolation. And it's joint work with my former PhD student, Alma van der Merwe, who's now at the University of Pretoria. So, yeah, there we go. There are roughly two parts to my talk. The first one is sort of a bit broader and talks about Nevanlinna-Pick interpolation, history, and some applications. And I'll motivate why we look at things like matrix point interpolation, why that's important. Second part is more related to the work that we did and a specific problem that we focused on. So yeah, there we go. So the original problem is really a classical problem, interpolation problem in complex analysis, and it can be formulated as follows. You have a couple of points in the right half plane. I can't really sketch anything, but it's the complex plane, right half plane, right half side there, and a couple of values. And what you want is an analytic function f, which maps the right half plane into the right half plane. So it's sort of a self map of the right half plane, and that takes the specific values, the lambda k's, to the eta k's. That's what the problem is, and it was solved by Nevanlinna and Pick independently. Pick in 1916, Nevanlinna in 1919. Then there's later work, and here are some of the basic results about this problem. So one of the main contributions by Georg Pick is that a solution exists if and only if the so-called Pick matrix, which you can construct from the data as said there, is positive semi-definite. So it's Hermitian, and all the eigenvalues are positive, or non-negative, I should say. And then there are a couple of cases. Of course, you want to know, you want to describe solutions. So if there's, if it's positive semi-definite, but the determinant is not zero, that means that you can find a function, a vector in its kernel, then you can use that to construct a solution, and that solution is unique. And the other case typically is when the Pick matrix is positive definite, so all eigenvalues are positive. And in that case, there are infinitely many solutions. It becomes a much more complicated problem. And that's something that Nevanlinna solved about 10 years later. Okay, now you may say, well, okay, this is more, most of this work is more than a century ago. Why do we care about this? Well, for various reasons. So during this century, there have been many applications, mainly in electrical engineering, control theory, but also in many other disciplines. And I'll illustrate this with some somewhat concrete applications. There are also many extensions to more complicated interpolation problems, and that really came as a result of these applications. So this is like a sort of basis result, but from there you can look at a lot more complicated problems. And also from a mathematical perspective, analyzing these kind of problems has led to the development of a lot of interesting mathematical tools in interpolation theory, functional analysis, and also in matrix analysis. And I'll try to show a bit of that in my talk as well. So here's the first sort of field in which it has been applied in electrical engineering. Goes back to very old work of Foster, Cohen, and Brune. And the important observation there in around 1930s is that if you look at electrical specific electrical systems constructed from certain components, the functions always correspond precisely to the type of functions that appeared in Nevanlinna-Pick interpolation. So they map the right half plane into the right half plane that's related to stability, properties, and in certain cases also the imaginary axis is mapped onto the imaginary axis, except at points where you have poles. So that was a major breakthrough, and I think sort of like the starting point of where complex analysis techniques started used in electrical engineering. So that was a big thing, and I want to say a little bit more about Brune specifically. From a mathematical perspective, his result is maybe the most impressive. The others sort of observed that when you work with such a system, you get these kind of functions. Brune is the one who went the other way. He showed that if you start with such a rational function, you can always sort of reconstruct such an electrical system. And there's another reason for mentioning it. He's a South African. And actually he did his master and undergraduate master here in Stellenbosch, 2021. He was also in Potchefstroom for 1 year as a teacher. Then he was in Pretoria, and after that he went to the United States to do a PhD at MIT, and that's where he did his work. He stayed for a couple of years, but in the 1930s, the United States was not the best place to be. He came back to South Africa, was involved, from what I understand, in what's now the CSIR, but mostly in administrative roles. So he didn't really publish a lot after that. I should maybe also mention that he's one of the founding members of the South African Mathematical Society. That's nice trivia here, I think. And that his contribution is really very fundamental, I think, follows from one of his PhD supervisors who contributed his book on passive synthesis of passive networks to him as being the person who really sort of provided the mathematical principles of this field. So he's, even though he only worked and published in this for a couple of years, his contribution has been used. Okay, this goes the wrong way. All right. Yeah. So I mentioned Nevanlinna-Pick interpolation. That only got involved much later, and a paper of Eula and Saito. So I don't know any earlier references for that. But the idea there is as follows, and that really uses the work of Otto Brune also. Now that you know that these functions can all be linked to these kind of systems, you can use interpolation, Nevanlinna-Pick interpolation, to construct electrical systems which have certain properties by adding interpolation conditions. And then it's of course the question, how do you translate properties of your electrical system to interpolation conditions? And that's a whole story, which I'm not going to do today. So I want to mention another application, and that's more in control theory, and that's really was an application which did a lot for the development of Nevanlinna-Pick interpolation. So I'll give this is a very rough sketch of this. I do this actually in a postgraduate course, and it takes about 6 weeks to explain. So it's more an illustration of how complicated things get when you really want to do something. The idea here is as follows. You're giving an input-output system, where you have lots of different inputs, but they're divided into two types, a W and a U. Then your system is indicated with this G, and you have two outputs, Z and Y. And what you can think of them is your W is typically like a disturbance. Your U is a control input, so that's like a button you can push or something you can twist. And your Y is a control output, and Z is like a measurement signal. That's typically the thing you want to control. Okay, so you start with a system G, and it comes in this. So it's indicated by a rational matrix function, which we call the transfer function, and it's divided in this 2x2 case, mapping the different signals from to other signals. And the point is, you want this system is not nice enough, so you want to do some control, which comes in the form of this controller K. This controller K, and then if you close the loop, you get a new system, and the transfer function of that system is the function S here, given by this complicated formula. You don't have to remember what it is, but that's how it comes out. And the objective now is that that function, it's a matrix function. It should be stable, meaning no poles in the right half plane, and it should have sort of the matrix analog of what you have in the classical Nevanlinna-Pick problem. So function plus its adjoint should be positive semi-definite now in the right half plane, and you should have equality on the imaginary axis. The typical application of this is in this format is that there's some sort of energy balance in the system. That's what that condition there does. So it roughly means that all the energy that comes out, that goes in through your signal W, also goes out in through Z. So there's no energy storage inside, something like that. Okay, so that's the setup, and then after about 3 weeks of lectures, you get to you can show that if you can find a stabilizing controller, so without the extra conditions, then you can do a so-called Euler-Kuchra parameterization of the stabilizing controllers. And after lots of computations, you see that you can rewrite your transfer function of the closed loop system in an easier form, as we have here at the bottom. So now T1, T2, and T3, they're all rational and stable matrix functions. And Q is also a stable rational matrix function, but that's like the new parameter after your reparameterization. Okay, so don't worry about all the steps to go from one to the other. My point is that in this form, you can connect it to interpolation under some conditions. So here we have the model matching form, and now we assume that T2 and T3, the two at the side, are square, and their determinants are not uniformly zero. That means that you can invert them as rational matrix functions, and when you can do that, you can just solve for Q through the formula there. You look at S minus T3, and then you multiply with T2 inverse on the side on the left and T3 inverse on the other side, and that's what your Q should be, right? There's no other option for that. But now the problem is your Q has to be stable. Yeah, so that's the objective that you need to reach. And why would it not be stable? Well, you take the inverse of T2 and T3. And if these functions have zeros in the right half plane, that creates poles for your Q. And somehow you have to get rid of those poles. Okay. And well, that's where you get interpolation conditions. So you sort of change perspective here. Normally you think you want to get a Q such that your S has certain properties, but now you actually try to find an S such that your Q is stable. And that generates a bunch of difficult interpolation conditions. So just to give you an idea, if you, for instance, if your T3 has a 0 at C0, that means that you can find a vector V such that T3 C0V is 0. And that, if you look at the top equation, if you evaluate at the point C0 and you hit it with a vector V, then your function S has to satisfy this first equation there. Likewise, you get sort of left tangential interpolation conditions starting from the zeros of your T2, and then more complicated things can happen. if the zeros are actually higher order zeros, then you don't just have these conditions, but you get derivative constraints on your function s. And it can be even uglier. It can happen that you have a point which is 0 for both t2 and t3, and then you get even further derivative constraints and also some relations between your interpolation data points. So you don't have to remember any of this, but the point is that the moment you start applying this, you get into much more complicated problems. And the one thing maybe good to remember is the derivative constraints that come in. Why do I? Oh, yeah, okay. So we'll see them a bit later. So just a little bit of background. This connection was made sort of in the early 1980s, so this is also from a long time ago. But the development toward getting a solution using interpolation techniques took almost a full decade. So this is really a complicated matter. There are also many other applications like H-infinity or robust control, model reductions, and in all these kind of problems, you can identify certain interpolation problems of various degrees of difficulties. And again, maybe nice to mention, there was also a South African involved in this, David Limebeer. I have to admit, I didn't know until last week when I was preparing. He did his PhD at UKZN in 1980, but he's been for most of his life in the UK at Cambridge, Imperial College London, and Oxford. But apparently, I didn't know that until last week, he is back in South Africa when he retired, distinguished professor at WITS with an A1 NRF rating. I only knew him from his sort of standard book on robust control, but had no idea that he was a South African at that time. But yeah, he is back in South Africa. Okay. So I mentioned interpolation conditions, and that's sort of the basis for the kind of problem that we're looking at. What we're going to do is we look at matrix point interpolation. So, okay, what do you mean with that? Well, you're going to apply, you take your rational function and you apply it in a matrix instead of just a regular point. And for rational functions, that's easy. You just write it as one polynomial divided by the other one, and you just compute the value in the polynomials. That's easy. And then you take the inverse of your QA, provided that Q has no roots and an eigenvalue of A. That's all possible, and that works perfectly well. And then the interesting thing is what happens if you take your point, for instance, to be a Jordan block. So that's of the type here, your JK at a point lambda. And once you evaluate that in a rational function or even a more general function, provided you can, it has enough derivatives, in the value that you get, you see all the derivatives coming up. So this gives you a way, if you start with just matrix points A and B, you look for a function f that maps a matrix A to a matrix B. That gives you a nice way to include all sorts of derivative interpolation conditions at different points without seeing a lot of the technicalities. Okay. And so now I come to the formulation of the actual problem that we've been looking at. So the class of functions here is the so-called positive real odd functions. They're real rational functions, so it's real polynomial divided by real polynomial. They're positive in the sense that it maps the right half plane into the right half plane, as in the original Nevanlinna-Pick problem. There's some sort of odd property. If you look at this on the real line, it's actually an odd function, but the context here, it's in fact equivalent to the problem that we saw before, that it maps the imaginary axis, except for poles, back onto the imaginary axis. So it has that property as well. And then the problem is as follows: given two matrices A and B, we want to know when is there such a positive real odd function which maps A to B. Okay, and that seems a lot easier than all the difficult formulations that we had before, but that's only because it looks that way. So there's just a Pick matrix in that form, and this is how you get it. So the moment you start doing computations, it turns into the same horrible mess that you expect to get. So that's something you want to avoid. So I just wanted to flash this without really going into the details. And this is actually even a simplified form. In the real case, you have to, for instance, also distinguish between eigenvalues on the real eigenvalues or complex eigenvalues, which come in pairs, and then you get 2x2 blocks. It becomes a huge mess. So you don't want to use this. And that's the point here, that for as long as possible, you want to use the right sort of mathematical context to work in without going into actual computations. And in this setting, that's so-called convex invertible cones. I'll show you some examples, but this is the sort of general algebraic setting. So you have a subset of a unital algebra. It's called a convex invertible cone. If it is a convex cone, so it's closed under positive rays and multiply with positive constants. It's also closed under addition. But the real nice feature here is that it's closed under taking inversion. So if you have an invertible element, then the inverse must also be in the cone. And that creates a very rich structure for these sets. And then something we look at, for instance, are convex invertible cones generated by a set. So if A is a subset, or if it's a single element, then C of A denotes the kick generated by these elements or by that single element. So let me give you some examples, and then you'll see that this indeed applies to the setting that we're interested in. So we can look at convex invertible cones of rational functions, real rational functions. So I mentioned positive real. These are functions, rational functions that map the half plane, right half plane into the right half plane. That's an example, and it's generated by two functions, f1 and f2 there. The odd property is another thing which generates a convex invertible cone. And then if you have to, you can take the intersection, and that again gives you a convex invertible cone. So the PRO is precisely what we're interested in, and so this is the right mathematical framework to work in. And what's also nice, it's singly generated by just a function that maps C to Z. Okay, so that's the function side. Now the matrix side. Also, when you look at matrix algebras, there are many examples. And I should mention here, for most of my talk, it doesn't matter whether I work over the real or the complex. We'll just indicate it with F. Just toward the end, I may need to specify. So Hn are the Hermitian matrices. Pn and Pn bar are positive, definite, positive, semi-definite. We've seen all these terminologies. So they're important. Yeah, just some examples of convex invertible cones. The one is, which is important in the talk, is the so-called commutant. So you have a subset of matrices, and you look at all the matrices that commute with everything in your subset X. That's a convex invertible cone. And the other one is so-called Lyapunov solutions. So now we're given a single matrix A, and we look at all the matrices H, Hermitian, such that HA plus A star H is positive semi-definite. And people in applied math will know that that's these Lyapunov equations come up a lot in all sorts of applications. So that's another example of a convex invertible cone. Okay, so how can we use this? Yeah. So, well, here's the first comment. I mentioned already they have a very rich structure. It's not just rays, as you would expect from a cone, but here's how you can construct them. So you start with your base set A, take all the rays through that, and then you recursively construct the new elements. So you take the ones A0, and then you add all the invertible elements. Then you take convex combinations of that. That's your next step, and then you keep doing this procedure, and that generates everything. But there's no general closed formula for these kind of sets. So they're not easy objects generally to work with. Yeah. So how does this connect to this interpolation problem? Well, that's for the following reason. So I mentioned already the positive real odd functions. They're singly generated by that function. What I don't think I mentioned is these functions have no poles. Sorry, their poles and zeros are all in the imaginary axis. Am I halfway? Okay. So 23 minutes. Where am I? Okay, perfect. Good. Yeah, their poles and zeros are only on the imaginary axis. And now, if you the reason for this is that construction of the convex invertible cones. If you look at the convex invertible cone generated by a single matrix, provided it has no eigenvalues on the imaginary axis, that's precisely equal to applying positive real odd functions to that function. Because the way to see that is that they follow the same procedure as in that lemma. Okay. So from this observation, you can say now that if we have matrices A and B, A has no eigenvalues on the imaginary axis, then we have a solution to our interpolation problem. So there exists a function f that maps A to B. Well, that means that B is in PRO A, and so by this corollary, it tells you that B must be in the convex invertible cone generated by A in this mathematical context. Okay, does that help at all? I mean, convex invertible cones are not necessarily easy objects, so yeah, does that help to determine if B is that an actual easier problem? Well, it's easier in the following sense, that it gives us a way to obtain at least necessary condition, because the convex invertible cone generated by A is also the smallest convex invertible cone that contains A, and also the intersection of all other convex invertible cones that contain A. So the moment you find some convex invertible cone that contains A, then you get a necessary condition that B must also be in there. So for instance, as a consequence, B must be in the bicommutant of A, which are all matrices which commute with all matrices that commute with A, because that's a convex invertible cone and it contains A. So the question now is, well, can we identify other convex invertible cones that contain A? Because that will sort of narrow the set that your B must come from. And all right, that's where the Lyapunov order comes into play. I mentioned already the set of Lyapunov solutions, and the Lyapunov order works as follows. We say that B Lyapunov dominates A if each Lyapunov solution of A is also a Lyapunov solution of B. So we have this inclusion here on the slide. And the observation by Cohen and Lewkowicz from their 2009 paper is that if you look at all the set of all matrices that Lyapunov dominate A, that is also a matrix kick which contains A. So we now have sort of a further inclusion. The kick generated by A is in this intersection. And the conjecture that they made in this paper that at least under some conditions on A, that's going to be an equality. And that will tell you that, okay, well, B has to be in the bicommutant of A, but that's not so difficult. But this Lyapunov order will be sort of your condition to determine whether you can solve this interpolation problem. The condition on the matrix A is a bit technical. It's in terms of the eigenvalues, as it says here. It roughly means that if you look at the eigenvalues, if you have one somewhere, it cannot be on the other, and you sort of pull a line through zero, it cannot be on the other side. It comes up at various places, but you don't really have to remember it. Okay, so again, question here. Well, if we have this identity, if that's true, does that make it any easier? Can you determine whether B is Lyapunov dominates A? We'll come to that too. Okay, so to understand this Lyapunov order better, we look at the Lyapunov operator. That's just a linear matrix map which maps X to XY plus Y star X. And so yeah, this operator has the following properties. It's a linear matrix map. It respects adjoints, but Y the other, this is where Lyapunov regularity comes in. It's an invertible map if and only if Y is Lyapunov regular. And in that case, you can identify the Lyapunov solutions for your matrix Y by taking the inverse and looking at everything that comes from positive semi-definite matrices. So with that observation, we can now say that if A and B are matrices, A is Lyapunov regular, so we have the inverse operator of LA, then B Lyapunov dominates A if and only if this map where we compose the inverse of LA and LB is a positive matrix map. Now, positive semi-definite matrix, these two positive semi-definite matrices. Okay, that's nice. But the problem is that positive linear matrix maps are not nice. They're horrible. There's not a, well, you can characterize, but it's just, they're not nice objects to work with. What is nicer is complete positivity, which comes up all over quantum physics and quantum computing and anything with quantum. And that works as follows. It's a more complicated concept in a way, but a lot nicer to characterize. So a linear matrix map is completely positive if for any block matrix, so the Vij, where each Vij is a matrix of the right size, if you apply your L to each of the blocks, and if your original block matrix plus positive semi-definite, then your new matrix should also be positive semi-definite. When you don't know anything about quantum theory and you've never seen this, this doesn't feel like a very appealing condition. But it turns out that that is something which you can easily characterize by a theorem of Mandu-Cho from 1975. You can simply check it by, so what you do is you start with your linear matrix map. You define what's now known as the Choi matrix. So your block, it becomes a huge matrix, and each of the blocks is obtained by evaluating sort of a standard basis element of your Q by Q matrices with the point L. You make this thing, you check if it's positive semi-definite, then your matrix map is completely positive, and the other way around. Okay. Just to give you an idea, here's a way to characterize positivity in terms of the Troy matrix. It's positive if and only if this Troy matrix is Hermitian, and you have some sort of condition on pure tensors. The cross here is the tensor product or Kronecker product between vectors and matrices, and that's a way to characterize this, but it's not something which you can easily check in any way. So this raises the question, is it maybe the case that this map LAB is positive if and only if it's completely positive? The motivation for why that might be true is because we know in all the specific Nevanlinna-Pick problems that we've looked at that you can check it by checking positive semi-definite over matrix. So that looks like the Choi condition. So we were sort of hopeful that that would be true, but it's not that easy. So here's just a little bit of background of positive and completely positive maps. These were just the definitions before. Okay, not all positive matrix maps are completely positive, and the main example, the easiest example, is just a transpose map that goes wrong with 2 by 2 matrices, as you can easily check. Okay, well, that you can sort of cover, and then you can define completely co-positive, which means that that's almost the same definition, but instead of your Vij, now you have a Vji there. And that's sort of another natural set of positive matrices. Then the question is, well, okay, can you write any positive matrix as a sum of something completely positive and something completely co-positive? That works for 2 by 2 matrices, but that already fails for 3 by 3 matrices. So it's just not very nice. And you may wonder, okay, well, how bad is it? Does it sometimes fail, or does it always fail, or is it really bad? And just to point out to a recent paper, well, just from the title, there are many more positive maps than completely positive maps. That already gives an indication that it is really bad. What they do actually, they look at this sort of from a measure theory perspective. Of course, there are infinitely many, so you have to specify what you mean with many more. And they connect it to the problem of positive polynomials and polynomials that you can write as sums of squares. which is also a classical topic, and a lot of things are known about those. Okay. However, it is sometimes possible, and that was our first attempt at getting some grip on this, at least when you look at very specific cases where you have some sort of sparsity pattern, then you can prove for certain cases that they are the same. And the specific result so that paper actually didn't help at all with our problem, but nonetheless, we thought it was sort of interesting. The specific result that we needed was the following, and that's in terms of the so-called Kronecker expansion of the linear matrix map. So what you do here relates to the so-called vectorization of a matrix. Okay, well, there's a difficult definition, but what you should think about it, if you look at the matrix T and you look at all the columns and you just stack them into a long, very long vector, that's the vectorization. Then the Kronecker expansion sort of defines a matrix with your linear matrix map. And the way you do it is as follows. Your linear matrix map L acts on a vector. So you take acts on matrices. So you take a long vector F size Q squared, you unvac it back into a matrix, you apply L, get a matrix back, and then you vac it again into a long vector, and that's your linear map. It's maybe not completely surprising because it is a linear map on a finite dimensional space, so you have all sorts of matrix representations once you choose a basis for it. That's the Kronecker expansion, and I'll skip this result. But the theorem that we have is the following. If you start with a linear matrix map L, and you take its Kronecker expansion, capital L, upright capital L, if you can find a matrix C such that L is in the tensor product of the bicomutant of T, C with take complex conjugate everywhere inside with the bicomutant, in that case, positivity and complete positivity will coincide. So that's a very specific result, but it turned out to be something that's the right thing that we needed. So let me illustrate that that's indeed the case. So going back to the Lyapunov operator, as we defined before, we can concretely, this is a very simple example, so we can concretely compute the Choi matrix, which we don't really need, but also the Kronecker expansion comes in the form of this tensor product plus another tensor product, and that is really what we need here, because now if you start with your matrices A and B, A being Lyapunov regular, B in the bicomutant, the fact that B is in the bicomutant of A tells you that LA and LB are both in this set for our matrix A star. And then also the inverse of LA is in the same set, and therefore the composition of the two linear of the two matrices is also in there because it's an algebra, and that tells you precisely what you need, namely the matrixization or the Kronecker expansion of your linear matrix map LAB that we're interested in is in such a set, and therefore we know that whenever it's positive, it's also going to be completely positive. Okay. So as a consequence, so now we can sort of pull this back to our interpolation problem that we originally started with. So A and B, A Lyapunov regular, B in the bicomutant. We can actually characterize when B Lyapunov dominates A, namely we compute the Choi matrix of our linear matrix map, and we have to check whether it's positive semi-definite. And therefore we can also find the necessary, sufficient condition for when when we can find a positive real odd function that maps A into B, namely by checking this that this Choi matrix is positive semi-definite. How much time do I have? Okay, that's plenty of time. Good. So that gives you sort of one direction. So we want to know when can we find such a function which does this? Well, this gives you a necessary condition, and it's a condition that you can check. You can actually compute this Troy matrix and check whether you just look for its eigenvalues and see if that are all positive, semi-definite. It's not computationally, this is not an efficient way, and there's a lot more work on this, how you can do this in a better way. And that's where your Pick matrix comes up, the horrible thing I showed on slide number 4 or 5. But the point is to avoid that, we just want to have it in this way. So the part which is missing now to get the other direction is that we need to find a solution. This only tells you that if there exists such a function, we have positive semi-definiteness. What we need to do is, if this Troy matrix is positive semi-definite, how do we find a function f which solves your problem? And okay, this is a little bit technical, but just to give you an idea, what you do here is you assume that your Troy matrix is positive semi-definite, so your linear matrix map is completely positive, because we know that positivity, well, no, that's just because of the Troy matrix. And then that tells you that you have a specific form for your linear matrix map. It's called the so-called Choi-Krauss representation. So you have a used matrix C, size mn times n, and on the inside you have identity matrix of size m tensor x. That's just a huge matrix where you have the matrix x m times on the diagonal. So it has this form, again related to work of Choi, but also Krauss, which is a bit later. And you want to take your m as small as possible. And you can always do that. You can construct these things concretely, but I'm not going into that now. Then, assuming again that A is Lyapunov regular, we can do the following trick. We have the Lyapunov, so if we take a matrix X, we apply the Lyapunov operator to it. So then we just get the thing on the left-hand side. But now we can apply the Lyapunov operator of A and its inverse, and that gives us the linear matrix map that we're working with, LAB, with on the inside the Lyapunov operator applied to X, of A applied to X. You use your Choi-Krauss representation. This gives you a concrete identity in terms of these matrices, and then you take for your matrix R, you factor it in some way to two matrices R and R prime star, and this identity then translates to a sort of skew symmetric identity in terms of these two matrices, LR and MR, where your R can be any arbitrary matrix, and from there you obtain the following. So A and B, Lyapunov regular, B in the bicomutant, and Lyapunov dominates A. We have to make an additional assumption here, namely that the rank of the Troy matrix is equal to the dimension of the bicomutant of A. That's just for technical reasons. And then there exists a single matrix S of the appropriate size, such that tensored by IN, so that's again like S copies of N copies of S, times LR is equal to MR, and that identity should hold for any matrix R. And the role of the identity with MR and the LR gives you that this function, this matrix S, is skew symmetric. Okay. So there's a lot of technicalities here. And that's really what you need. So I'll just briefly, I'll just give you the theorem here. Once you have this matrix S, you decompose it in sort of a block column, scalar column, scalar row. That will give you a 0 there and a vector L and a matrix M, which is again skew symmetric. And from that, you can concretely construct your function in that way. And that it's so very quickly, you just use the fact that this matrix S satisfies the equation with L and the M. That gives you a bunch of identities, and from that you can easily compute that it's satisfied, that it gives you a solution. And that it is a PRO function follows from basic realization theory and the properties of the matrices. So it's specifically the skew symmetric part. So this is all a bit technical, I realize that, but this is a way to construct such a solution using standard theory from standard realization theory from linear systems. Okay, so and with that, you can then go both ways now. So A and B, A Lyapunov regular. I included this rank condition that we had in part of the proof, but we know through other results that we don't really need it. So what we then obtain is that that the conjecture is indeed true. B is in there exists a solution f to the problem positive real function f. So it's f a is b if and only if b is in the bicomitant of a and Lyapunov dominates a, and the latter one we can check by the Choi matrix criterion. So we have that, and that gives a full proof of the conjecture. So just some concluding remarks. The kind of problems that you work with here are extremely technical, and I couldn't really avoid having some technical slides on there. But by working through it in a sort of a setup where you use convex invertible cones, where you use matrices to sort of hide some of the technicalities, gives a nice approach to solving these problems without seeing all the difficult computations which are underlying it. I forgot to mention this on the last slide. I mentioned at the beginning that the problem that the way they formulated is for real matrices only, and most of the talk was for real and complex, but it was only on the last slide all of a sudden that I went back to real matrices, and that's because the realization result that we used does not really work that way if you have complex matrices, or it's not that easy. But you somehow need some extra spectral properties to get a positive real odd function if you work with complex matrices. It can be done, but it becomes an extra technicality. I mentioned also, so somewhere there was an additional assumption to make something work. That's not a completely, that's a serious assumption. And you can see that from the construction that I did on the last slide, you get a function which doesn't have a pole at infinity. But in this class of functions, for this class of functions, they're allowed to have a pole at infinity. So there are many examples that you can construct where you only have a solution with a pole at infinity, and in that case, that condition is violated. So we have other ways of showing that you can still get a solution, but that's another talk. But this method doesn't work in that way. You need to do something else. And in fact, that goes back to something on my first slide. I mentioned that you have there are typically two kind of results. You have the case where the Pick matrix is invertible, and that's sort of what we did here. Then you have the case where the Pick matrix is not invertible, and you can take a vector in the kernel, construct a solution from that. That's the other case, and in that case, you can have poles at infinity. That's a whole different way of reconstructing them. Okay, you can do this for matrix valued functions, and I with the second application, I mentioned that this is something which you may need. But I didn't want to do it in this talk because it's already difficult enough in this way. But you can extend it in that way as well. Let me not say too much about the discrete time case. Something that we're working on at the moment, and that's really interesting to us, is so-called multidimensional system setting, where you have systems that have multiple time axes, and you have to work with functions in several variables. And that creates a whole lot of extra complications here. But again, that's, well, we're not finished. That's still work in progress. So I want to conclude there. Thank you.
Thank you very much for a very interesting talk. Any questions from the audience or comments?
Andre?
I forgot now which theorem it was, and unfortunately you don't have numbers, so I can't point you to it, but maybe it was in relation to the Choi matrix. There was a theorem, and you end up having to show that something is positive.
Yes.
Definite?
Known as Choi's theorem. Then previous slide. This one.
That's right. How do you test for positive definiteness and positive semi-definiteness? You said compute eigenvalues, but of course that's not really practical. I assume these matrices are big.
Yes. It's a good question. What's moreover, I mentioned somewhere that this is not practical to compute. So we can say, okay, well, this is your condition to see if solutions exist. In fact, the matrix is huge, and it's to give you an idea. If you work with an even a standard n-point interpolation problem, the size, it's going to be an n squared by n squared matrix with lots of zeros. So that's not what you want to do. And yeah, we have one paper sort of on this where you can use different representations and different ways of computing this matrix, or let's say like the actual Pick matrix is sort of hidden in there. And there are sort of more efficient ways of computing that. But I understand what you say. Computing eigenvalues is numerically, that's not probably the thing you want to do.
What I'm driving at is if you just have an ordinary n by n matrix and you want to check positive definiteness, then you don't need to compute eigenvalues. You can check if it's as a Cholesky factorization.
Sure.
And that is a finite procedure, which is much simpler.
Yes.
Yeah. Yes. So I don't know if there's anything similar in this.
Yeah. I mean, Cholesky factorization is something you can do. I don't know if it's. It would be. I mean, like I say, the complication you have here is that it's a huge matrix with lots of zeros. It's a very sparse matrix typically. So I mean, yeah, it's n squared by n squared matrix of rank n normally, or less. So that gives you some extra complications, I think. Yeah.
Any other questions or comments? Are there perhaps some questions from the online audience? Could we? We did. Thank you.
Just give us a sec. So it's from an anonymous attendee. They ask, what is the product or multiplication of the unital algebra, which are CIC? Not sure if that makes sense.
So what is the, come again, what is the product and the?
What is the product or multiplication of the unital algebra, which are CIC?
I mean, in a general setting, you work within an algebra, and your convex invertible Cohen is like a subset of your algebra. So it is whatever it is that you work in. And in the examples that I showed, so we have the real rational matrices. So then it's just multiplication of real rational functions. So then it's just multiplication of rational functions. And the other examples that we have is with Hermitian matrices or other matrices. and then you work with matrix multiplication. So you adopt the operations from the algebra that you work in.
Perhaps I also would like to ask a question. So most of the time you were working with matrix algebras. I'm wondering how much of, especially the key techniques to proofs can be extended to general algebras, not necessarily matrix algebras.
I'm not sure. I mean, some things I think you can probably do at a more general level.
But people don't really, it's not interesting thing to do.
Yes, maybe. I mean, we came to this problem from a very specific and concrete application, so it was sort of natural to work into this setting. But as like I said, I mean, as objects, but within some general algebra that they're interesting to study as well. And I mentioned somewhere in the beginning, but that's I'm trying to think now what's going back to their papers. So maybe there are some general results, but they very quickly sort of go to matrix algebras and function algebras. But for instance, I mean, there's like a general construction, how you construct them, at least recursively. Yeah, I'm not aware of papers that study this more generally.
So maybe if you've got algebras with other norms on them or something like that. So when you did your very first definition, isn't there a condition on the boundedness of the norm of the analytic function or the Nevanlinna-Pick?
Mm-hmm. Yeah. But it's I mean, you get a connection with sort of with a norm because you work with a code. So in the context of Nevanlinna-Pick interpolation, what sort of relates to a norm is that it maps the right half plane into the right half plane. Not so obvious maybe there why that's a norm, but if you look, for instance, so I didn't mention, it was one of the points at the end, but if you look at sort of what happens when you look at discrete linear systems and sort of the theory that you get from that, you don't look at functions which map the right half plane into the right half plane, but you look at functions which map the unit disk into the unit disk. And then it connects directly to a norm, namely the supremum norm should be bounded by 1. So in that setting, it's more natural to look at norms. Yeah.
Well, before we thank the speaker again, I would like to present him a small gift from NITheCS. This is a Visarku journal. This specific volume is called Mathematics for Everyone. Visarku journal is founded and led by Professor Sophie Marquez. It has interesting articles from students, from professors.
Thank you.
And for those attending in person, I'd like to invite you for some refreshments right after this.